Welcome to the second part of the lecture. In this part, we will do another problem involving, this time, non-bounded operator. Problem. I'm sorry, I have to change it. Yes. And we have here the following. So suppose we have a Banach space. E is a Banach space. And we consider an unbounded operator. This is my, sorry, I have to make it a little like that. D of A contained in E, and it goes to E star. Suppose that is a densely defined operator. Then show if there exists a constant C larger than 0, such that for every x belonging to the domain of A, if we have here that x is larger or equal to minus C, and here we will put here ax to the square, call this condition 1, then we have that kernel of A is contained in the kernel of A star. So let's do the solution. First of all, notice that A star is basically also an unbounded operator, which is defined on the space E double star, and it goes to the E star. And since we have the duality, there is a duality, there is a duality map, we call it J, that is going from E to E double star, that allows us identify E with a closed subspace of E double star. Therefore, the inclusion, call it inclusion 2, makes sense. Makes sense. Okay, so we need to show So take it that a kernel is contained in the kernel of the adjoint operator. That means take x that belongs to the kernel of A. Let's move down a little and assume that, call it y, belonging to the domain of A is arbitrary. And in addition, take t larger than 0. Then, by condition one, we have, and this is simply, let's write it down, ax plus ty applied on x plus ty is larger, equal to minus c, and here we have here a, and this is x plus ty, close it, put here square. But remember, x was belonging to the kernel. This is the kernel of A, therefore we can rewrite it, and this will become, in this case, nothing else. Then we are getting here that this will be t, and this will be a y, and this is x plus ty is larger, equal, maybe don't need this, let's write it here, is larger, equal than, again, minus c, and here we have here a t y square, which leads to the following, which after simplification gives us, leads to, and let's do it clearly. So this will be the thing that means this is equal, and that one is equal a y x plus, and here we have here a, put here t, maybe not so nice, put here t, and this will be a y is larger, equal to minus, and here we have also c, we have t, and this one is a y square. So we can put, we leave that guy here, we have here a y, and that one is here. So we are getting here that this is larger, equal than, that one is t, and what do I get here? Minus, put here minus, and then here I get having a y, and that one is plus c, and that one is a y square. And notice that here this inequality is true for every t positive, for every t positive. So therefore passing to the limit, as t goes to 0 from the positive side, we obtain that, okay, for every y belonging to the d of a, we have that a y x is larger equal to than, say it, 0. However, notice, but look, since a linear functional, let's write it down, functional, this functional, a, y, x is linear, then of course the image of this function cannot be bounded from below, only in the case of this functional being 0. So that means, since the image of any linear function is a subspace, the subspace is bounded if and only if this subspace is 0 subspace. That means we have here a y of x must be equal to 0 for all of them. Which implies that x belongs by this condition to the image of a perpendicular, and since this is the case of a joint operator, we have here that must be equal to the a star, and therefore our conclusion follows. So put here end of the problem, and I hope that you followed and you had an opportunity to enjoy. And next time I will do a couple of more problems. Please remember, this is not yet a lecture, this is just a practice. I'm trying to practice my presentation. I'm trying to learn how to deal with the technology, how to operate this tablet, and maybe we will see that in future it will become more smooth. Thank you.